Ma'am, shall we start now?
Okay, yes, ma'am, definitely.
Ma'am, can you switch on your camera? Ma'am?
Yes, just give me a moment. Is it visible now?
Yes, ma'am.
Okay. Maybe if I get less bandwidth, I may be switching off camera when the video and all will be there in the PPT.
Right, ma'am, that is no problem.
Ma'am,
I'll just introduce you, ma'am.
Yeah, sure. Yes, sure.
Good morning to all the participants. Welcome to the second session of FDP. So today our speaker for this session is Dr. Sumita Mishra. She is an assistant professor at Amity University in the Department of Electronics and Communication Engineering. So her personal statements include, as a professional, she is working in the field of engineering education. Her primary duties have included teaching, research, and mentoring engineering students. Major expertise is in the field of optical and wireless communication. She is very passionate towards learning new cutting-edge technologies and trends in engineering. Positions that she has held so far includes that she is an assistant professor grade 2 in electronics and communication engineering department at Amity School of Engineering and Technology, Amity University, Lucknow. She was also a lecturer in electronics and communication engineering at Amity School of Engineering Technology. Ma'am has quite a few memberships in the professional societies, which includes senior membership in Institute of Electrical and Electronics Engineering. She is a member of Institute of Engineering and Technology UK, member of International Association of Engineers, member International Association of Computer Science and Information Technology, various university committees and tasks that she has taken up. She was a single point of contact for National Program on Technology Enhanced Learning, which is called as NPTEL in our country, for engineering institutes in university in the year 2018. She has also listed in quite a few major activities, which includes departmental committee members, program leader, departmental committee member for quality assurance, department SRC member. Other experience includes she is a reviewer and editorial board member of Valaik Journal of Science and Technology, International Journal of Machine Learning and Computing, IAES International Journal of Artificial Intelligence, Bulletin of Electrical Engineering and Informatics. Ma'am, we are very delighted to have you here. And ma'am also holds quite a few publications to her credit at various journals of national and international repute. So on behalf of the Department of Biotechnology, the Oxford College of Engineering, I, Salma, Assistant Professor at the Department of Biotechnology, take it a pleasure in inviting you and welcoming you to today's session as our guest speaker. Ma'am, welcome again to the session, ma'am. And you may please take over the session and start it.
Okay, thank you so much, Salma Madam, for such a comprehensive introduction. So I'll be starting with the talk today. Basically, my topic deals with thermal infrared imaging. All of us are familiar with the conventional imaging, but thermal infrared imaging is somewhat different from the conventional photography that we see generally. So thermal imaging is different in the sense that thermal imaging uses infrared wavelengths. Okay, so instead of visible wavelength that we use in normal cameras, we use infrared wavelength in thermal imaging. So this kind of energy is not visible to our eyes, and we can broadly classify infrared into three regions. First one is near infrared, then mid infrared, and then far infrared. So how this technology is used, basically every object that we see around us emits IR radiation. And this intensity of radiation emitted will be proportional to the temperature of the object. So that means that if you have a hot object, it will emit more IR radiation. You have a object with less radiation. So sensors in a thermal camera, what they do, they capture these emitted radiations. So these emitted radiations are captured by the sensors in the thermal camera. And that is the reason, that this kind of technology works in complete darkness also. So let's see it with an example I have shown you in this. So here you see that there are two glasses of water. So if we have a look at them, these two seem identical to us. But if you take a thermal image of this particular scene that you see on the right hand side, then you can visualize that the first glass is that is towards the left side glass is having higher temperature compared to the glass which is on the right hand side. So this kind of information can be easily inferred by thermal imaging. So now this kind of technology can be used for applications where basically the temperature difference can provide us some useful information. Right. So now let us see at a typical setup of a thermal imaging system. So here you see the typical setup where there is a lens with optical assembly. Now lens here is not same as the lens that we use in normal cameras, because the energy being used here is infrared. So the lens should be transparent at infrared wavelengths, right? So we cannot use glass because the glass is not transparent at infrared wavelengths. So some typical thermal lens material that we use are germanium, zinc selenide, barium fluoride, and so on. There are many materials that may be used here. Now, one more thing that should be kept in mind here is that resolution of thermal cameras is much less compared to the normal conventional imaging cameras. Why is it so? Because as you see here, this lens will focus the energy onto a IR sensor. Now the sensors that we have here are working at a greater wavelengths. So the size of the sensor is large compared to the sensors at the optical wavelengths. So that is why the resolution generally found with these cameras is low compared to the resolution found in normal imaging devices. Right. So in a nutshell, you see the setup, what is there. It is made up of this lens I told you about, then an optical assembly. After this, you see a thermal sensor or IR sensor, and we have some processing electronics, and all this is cased in a mechanical housing for use. Okay, so that is the typical setup. You may have many advanced systems with included other circuitry, but this is the general description of a setup, right? So here in this diagram, you see some typical thermal cameras which are used for various applications. So these are depending on the applications, you can select a particular camera. So if you are looking for a application where you want a camera which is having very good resolution, or you want to capture temperature differences which are very small, then the technology of choice will be the cooled thermal camera. See, these cameras are of two varieties. One is cooled thermal imaging cameras, and the second one is uncooled. Cooled and uncooled are having different variations on the basis of this thing, that detectors in cooled ones are using some kind of cryo setup, so that the noise in thermal cameras can be reduced to a very small value. So that is why the performance of cooled ones is much better than the performance of uncooled thermal cameras. So this first camera that you see here is the handheld one. This handheld camera is used for outdoor applications mostly. And the second one is also outdoor one with the zoom in and zoom out features. Third camera you see here is having the facility of recording also the thermal images captured. So that is also a different one. Then the fourth one can be, this is by Fleet. This can be directly integrated with the smartphone with the Android setup. So this kind of camera is very useful for certain applications, and it is not that expensive also. So this is generally people use for some research also. Then the last one is a very powerful camera which captures the minute variations in temperature, and this kind of camera is capable of providing displays on these large monitors also. So the next thing that we will see that why we are having so much interest in thermal imaging these days. So you may have seen that during the past decade, lot of research, new research basically has come out in the field of thermal imaging. So why is it so? So that is due to the amalgamation of these three key technologies: artificial intelligence, deep learning, and robotics. So now when you have these novel technologies, then these three technologies can improve the performance of thermal imaging system. And when the performance is enhanced significantly, then these two technologies can be integrated for many novel thermal imaging applications. For example, you must have seen during the COVID time that augmented thermal imaging applications, that is thermal imaging with AI, were so popular. So you are able to detect people with fever even in crowd. So how is it possible? That is possible due to the integration of thermal imaging with AI. So how these applications, new applications can be thought of? Maybe you have an application where some thermal imaging unit has captured some random event. Okay, so maybe for example, you can assume that you are recording a thermal image to see whether there is any intruder or not. Okay, so that kind of random event will have a different outcome every time, right? So one time you have one kind of outcome, in second instance you have another outcome. So when these non-deterministic problems occur, then there artificial intelligence can provide a successful solution. So we integrate thermal imaging with AI. Then let's just briefly go through description of AI, because there may be some people who may not be much familiar with this concept. So AI is basically the creation of software that can imitate human behavior. Okay, so the capabilities of human and human behavior can be implemented with the use of AI. So based on the past experience, like the humans have some experience in a situation, AI can also make a decision. It gets the data and adds past experience to it, and using this, it can be used in applications to detect anomaly in a situation, to interpret any visual input, what kind of information is there, and it may also be used to understand written and spoken language. The uses are a lot more, but I have listed some very general uses of AI. Then you have one more branch of AI. You can assume that it is one of the flourishing research areas. This is a specific subfield of machine learning. Basically, I am working in this domain, so I am more interested towards this technology. So deep learning is different from machine learning in the sense that in machine learning you give handcrafted features. Okay, you derive the handcrafted features, you give input, and these features you derive, and based on that you create a model. But deep learning is end-to-end learning. End-to-end learning means that you give an input to a deep learning model, and at the end of the network, you will get a result. Okay, simply you do not have a typical pipeline architecture that you see in traditional machine learning algorithms, but that is also having incredible accuracy. Sometimes these algorithms are surpassing human level performance also. Okay, so this end-to-end learning is the biggest advantage of deep learning. So deep learning is basically capable of extracting the features automatically. That is also one thing to note. So a simple description is shown here. So you see a network with initial layers will have features which are very simple. It derives simple features. Then as you move towards the later layers, the complexity of features derived is more. Okay, so and you can add a classifier at the end to get the result. So that is also a key technology that is changing the thermal imaging domain. Then next thing that we see here is robotics. Okay, so third key technology, robotics, is also enhancing thermal imaging applications. So what you see here is a robot which is used for harvesting strawberry in a farm. So this, you see that there is a hydroponic system, and the strawberry grown here are automatically being harvested. So in this kind of robotic setup, if you plant a thermal camera, then thermal camera can detect whether the strawberry is ripe or not. So if you include this functionality in this, then area where you have strawberries which have not ripened, that area may be left by robot. So this is a novel application. So that is how these technologies, deep learning, artificial intelligence, and robotics are giving us new areas to explore in thermal imaging domain. So next thing that we see here is another application of thermal imaging, but this kind of application is used for security. So you see here a system where this system is having two kinds of camera. This is being developed by a security company. And in this kind of setup, what they have done, they have two kind of imaging available in the robot. One is normal imaging that may be used for daytime. Then they have a thermal video surveillance setup also in this. So this can provide you the detection of people and cars at night also without any artificial light. Okay. So this kind of application is basically possible due to the combination of these enabling technologies with the thermal imaging. After this, we may discuss some of the applications of infrared thermal imaging. Here, the first application that you see here is basically outdoor monitoring. So as you can see that outline of people who are there is visible because there is a temperature difference between the humans and the surrounding background. So this kind of difference is there. So that is why you can detect people. And the second thing that you see here is basically detection of a process in any materials which are being looked for defects. Okay, so in this condition, you see that this kind of evaluation of materials is non-invasive and non-destructive, because you can see that delaminations in the figure B, you see that delaminations are appearing as a hot spot. I have circled it also, so you can see that there is this delamination. Okay, so delamination is basically a failure of material when the material is fracturing into different layers. So lot of materials are made from laminate composites, and then they can fail, and this delamination, if detected, then you can replace that material, and you can use this kind of thing in factory setups also. So this kind of application is being used in manufacturing units. Okay, and the third application that you see here is also applicable to factory setups. This is known as condition monitoring. So what is condition monitoring application? It is basically about maintaining equipments in a particular factory setup. So in any kind of factory setup, this is one of the critical tasks. So now the inspection with the thermal imaging devices is being used to ensure the smooth operation of equipments. And these thermal imaging devices nowadays, these are so sensitive, and the cost is also less, so they can recognize subtle signs of failures before they can, before any kind of failure occurs. Okay, so this kind of application is also quite being explored nowadays. Then the next one is basically the medical application of thermal imaging. We will be discussing this application in more detail also. But for the time being, this is the particular setup where you use it to see that this is the foot of a diabetic person. So due to diabetes, the proper blood circulation is not there. So that condition is visible here. So that was some of the applications of infrared imaging in various fields. So next we are going to go into a bit more detail about the medical applications of thermal infrared imaging. Here you see that one of the best things about thermal imaging is that it is patient friendly because it is non-contact and non-invasive process. Okay, so initially thermography or thermal imaging was not an accepted norm in medical domain, but nowadays slowly, especially in breast cancer domain, it has been recognized as an adjunct technology for use in other modalities, like you can have mammography, but apart from that you can also have thermal imaging as an assistive setup for any cancer patient. This has gained a lot of acceptance in various countries, and in some of the countries it is accepted as a norm also. So, as I said, that it is patient friendly, and this is capable of being integrated in many applications. Then, the biggest use of this technology is in various disease recognition, because thermal imaging is capable of capturing even the smallest temperature differences in high resolution. So nowadays, thermal cameras with temperature difference of 0.1 degree centigrade calibration are available. So this kind of temperature difference can be easily recorded and analyzed by thermal cameras. So it is a big market over there for use of thermal cameras. So, particularly in medical imaging applications, you can use this for three basic categories. You may use it for disease detection because based on the blood flow variations in the body temperature changes, and skin temperature is changing. Then you can create a model to find the anomalies there. Okay, and these anomalies can be examined, and you can find out various diseases, primarily breast cancer or detection of some kind of tumors in the body. Then you may also use it for monitoring of certain conditions. Then screening, all of us saw the use of thermal imaging in screening during the COVID times, because it can capture the temperature difference very, very readily. So these are the three categories, and I'll be taking up some of the applications in detail. So what you see here is basically the thermogram of this of a female person who is suffering from breast cancer. So in the left one, you see that there is normal distribution of blood flow. So this kind of thing is used as a control information, and then the anomaly with respect to this can be evaluated and detected. So the next thing that you see here is the image of a particular setup. What they did here, they tried to increase the sensitivity of thermal imaging. So how did they do that in this particular experiment? What they did, they put the hand of the person on ice for 30 seconds. So after the hand was put on ice for 30 seconds, it was seen that if you take the image of that particular person, you can see that sensitivity is increased to a very high degree. And in the second image, that is B image, you can see that even veins of that person are visible clearly due to this kind of stimulation. So in thermal imaging applications in medical domain, what we generally do, we allow the person to we put the people in AC and cool down their body temperature, and when the temperature is becoming normal after this, then it is observed that the sensitivity of capturing the anomalies is increased a lot. So this kind of setup is also being used by many people here. So that is one thing which is being explored. Then here you see that there is a subject and that particular person was using handheld camera for some time. So in the first image A, you see that the person talked on mobile phone for 1 minute. So after this, you can see that there is not much thermal change that has occurred. And in the second one, in the second image with the arrow, it is shown. You can see that that the temperature change is large, right? So why this large change is there, and what are the after effects of this? These kind of research areas are being explored in thermal imaging domain. Okay. So it was seen that after talking for 15 minutes, the temperature rise was 4.59 degrees centigrade. So that is a phenomena that needs to be evaluated. So initially the temperature was 30.56, and after the talk on phone, it was raised to 35.15 degrees centigrade. And the temperature in ear region is not raised that much, but there is also a significant rise. So due to high sensitivity of these thermal cameras, these kind of areas are being researched. Then we will take up one more example here. So this kind of example you see here, that is a person with diabetes. So you see here that blood circulation will be slow in a diabetic person. Okay. So now this kind of low blood circulation can be visualized on thermal images. And you see the encircled region here. So this region, which is shown by a dark circle here, this region is having temperature difference with the surrounding region. Okay, so this kind of temperature difference is due to the presence of varicose veins in diabetic people, and it also was confirmed with the other diagnostic methods that there is a mild inflammation here. So in the second part, you see that there is the temperature profile of the person, which was obtained after thermal imaging. So in this, you see that this kind of temperature profile is basically can be inferred from this kind of profile that the person may be suffering from pain also due to this varicosity. So during the experiment, the researchers confirmed, you can see the research listed there. Researchers confirmed that there is the correlation between the thermal findings and the clinical diagnosis. So this kind of research can be used for detecting the anomalies in food due to diabetes. Diabetic evaluation of people using thermal imaging is one of the most explored areas. You will see a lot of paper on this in this area, and lot of research is going on breast cancer detection using thermal imaging. So these are the two areas in which a lot of previous research is available. This is also a particular setup that was done to evaluate two diabetic subjects. One is having the normal value of HbA1c, that you know that it is basically 6.6 value is normal, and the other person, the part A shown here is having diabetes. So this kind of difference can be used to detect diabetes in a non-invasive manner if you use thermal imaging for this kind of detection. Right. Then these are some of the applications which are not much explored, but some kind of literature is existing in thermal imaging. So if there are any people who are interested in this area, then they can explore these emerging areas in detail. It may be used for dermatological applications and for rheumatic diseases and sports injuries. There is some work which is there, but a lot of possibilities are there in developing new models and new solutions in this domain. Then for neuromuscular skeleton diagnosis also, a lot of scope is there, and recently some literature is there on detecting eye diseases using thermal imaging. So all these are emerging areas in which a person who is entering into this new field can work. Then let me show you a small video before we go into the details of applications of thermal imaging in agriculture. Uh, is are you people able to hear the audio also?
Yes, yes, ma'am. It's audible.
Okay. So that was one FLIR camera, which is basically one of the leading thermal imaging sensor providers. So that kind of camera can be equipped on a drone or helicopter to get the imaging of a particular area in which you are interested. So thermal imaging is also having a huge scope in agriculture also. So I have listed out some of the possible areas where we are using thermal imaging in agriculture. First one is irrigation scheduling. This can be used because if you have a plant which is having water stress is basically detected through thermal imaging by using this kind of setup because what happens that stomata in the leaves will be controlling the water evaporation, and when the water is being evaporated at a fast rate, then as the stomata will close, then leaf temperature will increase. So now this change in leaf temperature can be detected, and you may have images of that particular area when there was no water stress. So you can compare it and find out that whether water stress is there. And if it is there, then you can automatically schedule the irrigation in that particular area. So this kind of thermal imaging application is being used. Then some of the research is there on soil salinity detection also, although not much research is there, but some people have done research on detecting the effect of salinity on plant growth. So soil salinity basically causes the impediment in crop growth, and when you examine these images with a normal reflected camera, then you cannot obtain this kind of features which are required for soil salinity detection. So here thermal imaging can be a very useful technology. Then the other study that is being done, this is the third area, disease and pathogen detection. This is one of the widely explored areas. There are many people who are working in this area, and you get a lot of literature in this. So that is a useful area also. Then a new use of thermal imaging is being explored in the maturity evaluation of fruits. Okay, so there are certain fruits and vegetables, you can find out whether they have matured or not using thermal imaging. So this kind of thing is basically used for automating also, so that automation can be applied. Then bruise detection is also an area which is being explored, because by visual inspection sometimes you cannot tell whether there is some degradation in food quality. So most of the technologies being used here are either by ultrasound or a pressure tester is used, but this pressure tester will destruct the particular object which is being inspected. So this non-invasive technology of thermal imaging can be used here for bruise detection also in fruits and plants. Then these are some of the areas in which people can work. Now I would like to discuss some of my work that I have done in this thermal imaging and this kind of field. So this is one of my recent publications. This work we did last year. So what we did here, we applied the deep learning technology to the thermal images which were taken from a benchmark data set, DMR data set. This data set is available on request. So after request, we got this data set, and it is having images for the people, healthy people and infected. Total patients here were 66. These were from 29-year-old to 85-year-old female who were having breast cancer. So the database was such that there was different shapes and sizes, and it was captured using the Fleet SC620 camera. This particular camera has the resolution of 640 cross 480 images. So we worked upon this data set to obtain the inference whether the image being analyzed is cancerous or non-cancerous. So how we proceeded, basically you see here on the left the typical images from the database. And this gives the some details about the data set. So total healthy subjects were 43, and 67 people data was there, but out of this one was discarded. So this we removed from our setup. So total number of sick patients age-wise are also listed here. This information was provided to us by the people who created the database. So we used a deep neural network for realization of this model. So deep neural network is basically based on neural networks only, but the difference is that number of layers between the input and output layer is very large. That is, in our network we have used 14 layers and 12 hidden layers. So what you see here in the diagram, on the left side you see these square nodes. These are basically input layer or input nodes. So input nodes transmit the information to the next nodes. You see these circular nodes. These are the hidden layers. Then the last layer is known as the output layer. Now, output layer will provide you the final result of the network. If you have trained the model for classification, this layer will give you whether the image that you sent as input is cancerous or non-cancerous, or if you are using it to diagnose a variety of objects, it will tell you what object you have fed as an input. Okay. So these are input layers, and then in between you see hidden layers, and this is the output layer. So deep neural networks are typically made from a large number of hidden layers. So any neural network which is having more than 2 layers can be categorized as a deep neural network, but actually in implementation, deep neural networks have a lot of layers, right? So this was the architecture of a typical neural network, right? Now here in this diagram you see a typical artificial neuron. These are the input and this is the weight. Okay, what is weight? Basically during the training of neural network we are trying to determine the weight that will help us find the relation between input and output. So this kind of weight determination is very important. During the training process, we are trying to find the weights only. Then we have another term known here in this literature. This is known as bias, and this is the activation function, which is basically one of the most important functions in this, because this activation function is important in selection of any kind of network, because when you are forming the network, then activation function should be properly chosen. So there are a lot of activation functions which are available, which you may use for creating your network, but ReLU is one of the most popular activation functions, and we have used ReLU only for our implementation. So the first one you see here is a sigmoid function, then the second one is the ReLU function, and the third one is tan-h function. So ReLU function basically what it does in this layer, when you feed this an input, it will give you a probability, okay, a probability at the output between 0 and 1. This value will be provided to you. Okay, so the last layer, classification layer, will have some kind of activation function only. So I will skip this thing because we do not have much time. So CNN architecture is basically one of the most popular architecture for imaging applications. Why? Because it uses this property of images, that in images most of the pixels nearby a particular pixels are having similar qualities. So we are not scanning the whole area, or what we do here, as you can see in the diagram, these two inputs are being given to this one element only. These and the other two inputs are being given to this one element only. So when the input is being passed to the next layer in convolutional neural networks, then it is sparsely connected. Sparsely connected means that in a typical neural network, what you do, all the inputs will be connected to all the hidden layers. Okay. So what you see here, that all the inputs, that means you say that input connected is weight 1 will be connected to one hidden layer node, then this input will also be connected to this, and so on. But this is basically a very efficient method, because in this what will happen, you will have less parameters. Okay, so benefit of this will be that what will be the benefit of less parameters? You will require less computing resources. So you see that, as I told you, that deep learning is end to end. It gives you very good results. So why not everyone is using deep learning? Because it requires huge computing resources and it requires huge amount of data also. So as you saw in our case, the data was less. So what we did the augmentation. Augmentation is basically a process to increase the number of data points using various technologies available. So that kind of thing was done here in this. What we did, we increased the images by using this augmentation method so that we can feed these images to our convolutional neural network. Some other operations that were involved in our design of neural network were pooling, activation I told you about, then dropout. So convolution, as you saw, it is basically depicted here in this diagram. What you see here, as you all know that images are in the form of matrix, these are stored in the form of matrix in the system. So what you see here is a matrix which is there for maybe a red color, blue color or green color. So that if an image has all these three components, red, blue, green, then there will be three input matrices which will be there, right? So you see here that this is one matrix and we use the concept of filters here. So what is the role of filter? Filter is basically trying to determine the features or trying to determine the characteristic of a particular area in an input. So when you put this filter onto this input image, you multiply this 1 with 4, you multiply this 0 with 9 and so on. So you will get and add all these things, then you will get the result 2 here. Okay. So this is the convolutional operation or the convolution operation which is being done in the convolutional neural networks. So here three things are there. You see that input you gave a big matrix here and the result is a very compact is in the very compact form, and this kind of thing is useful because you see that a lot of nearby pixels will have same information which is there. Okay, so this information can be compressed by convolutional layer and can be only the important features or important information is passed on to the next layer. So this is basically very useful for imaging purposes. So you see here that the parameters that you need to specify for filters are, these parameters are, first one is size. So as you know that size, you can tell that this is 3 cross 3. Then stride is one parameter. Stride means that after you put your filter on this input image, then you need to scan other part of the image. So if you move by 1 pixel size in this direction, then you say that stride is 1. If you move by 2 pixel size in this direction, then the stride is 2. So stride is basically determining the way you are examining your input. Then padding is also one thing that is important. We will discuss it in a subsequent slide. Here you see that this is, as I said, that this is an input matrix for red color. Similarly, you may have matrix for blue color, so you will have a filter there. Then you have a matrix for green color, so you will have another filter there. So there will be a number of filters which are there. Okay, so it depends on the depth of the image. So what is the depth of the image? As I said, every image is made from red, blue and green component. So these are the three dimensions which are there. So that will be known as the depth 3. You can have multispectral images also in remote sensing or in thermal imaging. There could be more than 3 planes. Then you can have depth as 4, 5 or so on. So based on that, you will select the number of filters. So next you see here is padding operation which was done. Padding is basically in this image, if you see that if you have a stride of 1, first you will put your filter here, then you will move it by 1, you will put your filter here and so on. But if you are not able to scan the whole image, because one column is left when you are striding in this dimension, maybe the stride is 2. Then what we do, we add this zeros at the corners. Okay, so this kind of thing is known as padding. Okay, you put a layer of zeros here. Okay, so this is pad 0, that means this is the input in image without any padding. Here you have a padding of 1, here you have a padding of 2, and so on. So padding is basically done to get this stride done. Okay, so after padding operation, then you have pooling layer. Like I told you that CNN will extract the features from the nearby area. Then these features will be aggregated and passed on to the next layers. So this can be done in the form of pooling. Okay, so pooling is basically done to reduce the spatial size as you move along the network. Okay, so first layer will have large spatial size, then the spatial size will go down, down, down. So this is important because you cannot have too much parameters in your network. Okay, even if you design a light network, it may have a huge number of parameters. Okay, so pooling operation is essential after convolution. You most of the time do the pooling operation. So here I have shown you max pooling. You see in the top left corner 0309. So what you do in max pooling, you pick out the maximum value in the pixels that are there in the block. So I have put 9 here. After pooling operation, you will get this 4 cross 4 size is reduced to 2 cross 2 here. Why? Because these 4 blocks are after max pooling represented by this 9 here. Then in the second block you see 8, 0, 6 and 5. So what we do in this block, we take the maximum value from this. This is 8, so I have put 8 here. In the third block you see maximum is 4 and so on. You can use average pooling also. But the most of the times max pooling is very efficient. So we employ max pooling only in the design of our convolutional networks. So then nonlinear activation we will not discuss here. One more important thing about any deep learning network is that, as I told you, that it requires huge amount of data. And another problem of that is that it is prone to overfitting. Overfitting means that you give some data to the network, and this data is so well memorized by the network that rather than learning from it, it is basically memorizing the things in the input, and based on that it is giving you an output. So this kind of thing will give you a very good training accuracy, right? You will get 99% training accuracy. But when you will actually test your network on actual data, on test data, you will see that accuracy has dropped to 70%. Why? Why is it happened? So that is because there is overfitting. Now, this issue of overfitting is very, very important and it needs to be addressed properly. So that is why we use a dropout layer to reduce the overfitting. So this kind of problem can be removed by using dropout layer or some kind of regularization. Okay, but dropout, we found that it is one of the best solutions to reduce overfitting compared to regularization. So here you see the network that we trained here. This work we did on MATLAB. And in this we got a very good training accuracy, and after augmentation we were able to reduce the overfitting also. So now we are working on getting data set from hospital from which we have MOU, and examining that to find out the correlation between the person who is infected and it is whether we can detect it from thermal images or not in the early stages of cancer. Because in most of the data set that we used, that people were not in early stages of cancer, they had advanced stage of breast cancer, and This was confirmed by various modalities that they have cancer. So we will be working on detecting this thermal breast cancer in early stages using the thermal imaging. So this was our parameters. We took the learning rate to be 0.01 because if you take learning rate very large, then you see that your network is not training properly. So learning rate is an important parameter that needs to be kept in mind. And pooling, as I told you, we used a max pooling of 2x2. Then optimization algorithm was stochastic gradient descent, and the stride was 2. Okay, so this was the parameters that we have. This is also a work which we published last year, but it does not use thermal imaging. It uses normal images which were taken for training our neural network, and this was specially trained for real-time detection of disease. Uh, because as I told you, the deep neural networks have a huge number of training parameters. So they require large computing resources. So large computing resources may not be available on smartphones and the devices which are limited in computing power. So now in this work we tried to train a model which has less parameters, because in the previous case that we discussed huge number of parameters were there, but in this we tried to create a lighter model that can be used for real-time applications. So what we did here, let me go to the block diagram. So what we did here, we first trained our model on a system which was having GPU. So it was efficiently trained. And after training the model, we use a neural compute stick by Movidius, Intel Movidius, to create a lighter model. So now what is the benefit of these compute sticks? They basically have vision processing units on them. So you can run your deep learning model on resource constrained device also. Here in this case, we used Raspberry Pi. So Raspberry Pi is a small computer, but computing power of this is not large. So in general, you cannot run a good deep learning model on it. But what we did here was we trained the model first on GPU, and then we created a lighter model of that. This is the model that we trained on GPU. So you can see that it has got very good accuracy, and overfitting was also addressed. We used augmentation also in this. The total number of images were close to 4,000, and augmentation was applied. Then here, this is the visual representation for each of the convolution layers that we had here. Then what we did here in this particular model was, after it was trained on GPU, what we did, we converted it into a graph and created a lighter model, and then the graph was burned into Movidius compute stick. So the model was, a lighter model was there on Movidius, and then this can be run on Raspberry Pi also. So the next step was to transfer this model on an Android device. We are working on that, and we have got encouraging results in this. So this was one work. Then this is one accepted publication, which is basically thermal imaging assisted infection classification for brinjal diseases. What we did here was we created two type of data sets. One was normal images of the plant was taken, RGB images were taken. Then we use this FLIR 1 camera. FLIR 1 comes in FLIR 1 Pro and FLIR 1 domains. So this camera is basically easily interfaced with Android phone. So the way the RGB images were taken from the mobile phone only, then using the same smartphone, we integrated it with our this fleet 1 camera, and then this resulted in thermal images, and thermal images were also stored on the mobile phone. So we got two set of images here. Okay, so these two set of images were then analyzed to detect the infection in crops. Okay, so here the number of images were less, so we could not apply a deep learning algorithm here because it will not work well on less data, and we wanted to compare our result vis-a-vis the images which were taken from a normal camera, RGB images, and the images that have that are thermal in nature, right? So we have two set of data sets in there. So this is the methodology that we used to get our results, and then as you see here that two classes of images were there. One was healthy and one was non-healthy, right? And these are the thermal images of healthy and non-healthy leaves. These were taken, and then the database was prepared. So the first step was first you can see that on the left hand side we see this original image. Now in this contrast enhancement was required and cleaning was required. We did that. We use Wiener filter here, and then the next step was classification. So as I told you that we did not have a huge amount of data. So what we did here, we use bag of features algorithms here. So bag of features algorithm basically is in the domain of computer vision, is derived from bag of words algorithm, that is a well-known algorithm in natural language processing. But here we do not have words, so that is why it is known as a bag of features instead of bag of words. So the steps here are first the extraction of features for these two set of data, and then the codebook creation was done, and after that encoding and pooling of features were done, and then we got the results you see here. This is the methodology that we used here. For codebook we used k-mean clustering algorithm, and SVM resulted in best classification accuracy, so we have used multi-layer SVM here. And then you see this was the feature extraction process. Classification is shown here. Okay, yeah, this is the result that we got. As you can see, that surf was used to get the features, and only the strong features were kept, and we have taken only 500 clusters here. Okay, so you can see that a number of features here is this much as shown on the screen, and clusters using the k-mean. After this we did the evaluation of our model. As you can see that number of images is less, so but still we got a very good accuracy, and as you will see here that accuracy was much more in case of thermal one, because with such little data we got good accuracy of 87% in thermal domain compared to the 84% in RGB domain. And although our thermal camera had less resolution, then also we were able to obtain this much accuracy. So this is a very encouraging result. Now we are working on getting more images so that we can refine our model further and maybe apply deep learning to get better results in thermal imaging domain. So that was one work. So then this is also as I told you that in deep learning you require large number of features, large number of images, right? So that is a mandatory requirement. So in both our cases, that the works that I have discussed in the past year that we did, so in both the cases we created the network from the scratch. We designed or built the network, right? So that is possible when you have sufficient data. But in deep learning, there is one more technique that is known as transfer learning. So what we do in transfer learning means that you already have a very good trained network, but this network is trained on some data which is a universal benchmark data set. Okay, so most of the networks which are there, they are trained on ImageNet data set that has 1 million images of 1,000 classes. So it classifies these images according to the class. So you have these benchmark data sets and then standard networks which are trained on this data set. So in transfer learning, what we do, we actually refine these trained networks. What we do, we keep initial layers as same, but we retrain the later layers, because as I told you in the introduction that in a deep neural network, initial layers derive simple features. So in case of images, what are these simple features? These could be where are edges, where are the change in texture, and all these initial layers will be detecting these kind of features. So what we do in transfer learning, we say that the initial layers, let us keep these initial layers fixed, and we freeze them during the training process. And what we do, we train the latter layers. Okay, so these advanced layers are trained and initial layers are frozen. So this kind of transfer learning is beneficial in the sense that it is less prone to overfitting even if you have less data, because it is already trained on some data. Now you are making it useful for your own data. You take your biomedical data, you take your plant disease data, you train your model once again using that data. So that is a transfer learning. So this is one of the work which is recently accepted for publication, and there we have tried transfer learning, and we used a model MobileNet version 1, because MobileNet is a very light model, and this kind of model is basically capable of having good performance even in edge devices, that is in Internet of Things. If you are having devices which are resource constrained, so those kind of devices can also use this MobileNet. So this MobileNet has got the name MobileNet because you can run this network efficiently on your mobile phone also. So the next step is to create some kind of app to get the result on mobile phone only. So it is very efficient in the sense you can interface with the IoT devices, and you can get the information on cloud using your mobile phone. So the next set of work is towards getting mobile net trained on thermal data of the brinjal, as I have shown you. So this is the set of work that we are doing. So that was all. Thank you, and we will take up any questions if there are any questions.
Thank you, ma'am, for that informative talk. Participants, if you have any questions, please post it in the chat box or unmute yourself and you can question ma'am directly.
Sumita madam?
Yes, madam.
Yeah, actually your talk was very good. So now for agriculture application especially.
Yes,
So
ma'am.
my question is what type of camera, what type of how thermal camera,
Yes, ma'am.
how thermal camera will matter, because suppose it will be attached with a drone, so that some distance matter. That is my question.
There was some kind of disturbance, but what I understood that you are asking about the thermal camera that we use.
Yes, yes.
Yes, ma'am. So best will be to use a thermal camera by Fleet because these are inexpensive, not much cost is there, and they can be directly interfaced with any Android device. Okay, so because nowadays smartphones have very good cameras. Okay, so you can take pictures from a smartphone and then you directly connect this Fleet camera in plug and play manner with the smartphone. So the way you take normal pictures, in the similar manner, you can take pictures from thermal camera and store them in your smartphone. Because most of the thermal cameras, they do not have very good storage. So suppose you want to take 200, 300 images, right? So in thermal camera, once you take some images, then you need to transfer those images to the computer. Then you go there again and again take the images. So if you have this kind of camera, which can be directly interfaced with the Android device, then it will be easier for you to use that memory in your phone for storing or capturing these images. And the FLIR one that I have shown you about in our work that we use, that is capable of recording also. So that you can generate images later. So that I would say that you can go for that kind of camera.
Ma'am, with this camera image, can we differentiate between fertile and non-fertile soil?
Sir,
Development of a soil?
yes, sir. I have not seen this application, but maybe that is a good idea. Maybe there is some work on this, and we can explore whether it is possible to detect the fertility of the soil. There could be some features which may be explored. Definitely.
Because each crop will have its own required
Yes, sir. Yes.
nutrient level. So
Yes,
if
sir.
we can measure that, based on that, we can design a device which will deliver the fertilizer. In case if
Yes,
the
sir.
plant is requiring it, then we can deliver. Otherwise,
Yes.
there is no need of delivering it.
Sir, as of now, what the searches I have seen that you can derive the deficiency from the plant images. Okay, I have
So
still.
that is based on morphological symptoms, right?
Yes, sir. Yes, sir. Yes, sir.
So in
This
case
kind
if
of
we can measure
application.
it in the soil itself,
Yes.
because
Yes.
many of the time farmers what happens farmers will spray the fertilizer irrespective of the plant requirement.
Yes. Yes.
If we
Right,
can
sir.
tell them whether it is required or if we can differentiate between the different nutrients like NPK, in
Yes.
case if the plant is demanding only nitrogen and instead of nitrogen, we can avoid adding nitrogen into the.
Sir, you have given me a very good idea. I will explore that. It's the
Probably
benefit
you
of
can
having.
collaborate with us so that we will also learn it.
Yes. Yes, sir.
Because Preeta madam is there, both of us will be
Very
discussing
nice.
about this kind of application,
Right.
Yeah.
and if you can help us in doing some kind of demonstrable devices, so it will be
Definitely.
nice.
Yes, sir. Being an electronics person, that is one of my passions to create some kind of device out of any application so that it can be actually used. We should not only do theoretical research.
Yes, because generally our farmers, what they do, they purchase the fertilizer and spray it on the land. But they will not be knowing whether the plant is actually requiring it or not.
Right.
So it's
Right.
an unnecessary wastage of fertilizer and enriching the soil with more amount of chemicals,
Right.
and the cost is also involved in it.
Right, sir.
By taking the photograph, in case if you can tell them nitrogen is not required, nitrogen is already sufficiently there in the
Right.
soil, so they can cut off this nitrogen and they can put only the required nutrient, so
Right,
that
sir.
their cost and fertilizers can also be saved.
Very good idea, sir. We will explore this further.
Thank you, madam. Thank you very much.
Thank you, ma'am, for that informative talk. On behalf of Department of Biotechnology and the Oxford College of Engineering, I extend my heartfelt gratitude to Dr. Sumita Mishra for having accepted our invite and being a speaker for this session. Thank you, ma'am.
Thank you, sir.
Thank you, madam. Thanks a lot for accepting our invitation and explaining your research areas. And we'll be looking forward for collaborative research so that
Definitely.
biotechnology and EC can do together in devising it, developing it.
Right.
Anyway,
Thank
Prita
you,
madam
madam.
will be interested in it. So we can make an interdisciplinary or multidisciplinary concept, and we can put all our effort, devise a device which is actually useful for our farmers.
Yes, sir, definitely. Thank you so much. And it
Thank
was very nice to be involved in such a good research environment. You people are having so much interest in interdisciplinary research. That is, I think, the need of the day.
Thank you.
Thank you, ma'am.
Thank you.
Ma'am, you can exit, ma'am. Thank you.